Okay, so just for the sake of recording, we are at day three. My name is Dr. Sanawaz Tahir. Just doing a recap of what we have done up till now. In day one, we went through the hands-on strategy, search strategy. We went through Prisma guidelines, Prisma flow diagram. Then we went through data collection forms, how you can extract data from full text articles. In day two, then we went ahead and in day two, what we did was that we looked at the risk of bias, how to calculate the risk of bias for different study designs, at the same time, how to visualize the risk of bias using visualization tools. At the same time, we looked at what are Cochrane reviews. So we discussed the Cochrane handbook. Then we also looked at what is the qualitative analysis that we can do in systematic reviews. We also had a hands-on exercise on Ryan. So this is where we are at right now. Um, so I will still like to go through this slide one more time. So what are the key steps in conducting a systematic review and meta-analysis? And like I've said before, not every systematic review can be converted into meta-analysis, but every meta-analysis has a background systematic review to it. With that being said, every systematic review starts with a research question. A research question coming, for example, say you're interested in what is the cumulative knowledge about a certain topic. That's the sort of research question that is for a systematic review. The research question and the topic and the objective of systematic review, they follow something called as PICOS, which is participant, intervention, control, outcome, and study design. Study design of the included studies. And then in every systematic review, you first go to online databases. Normally, as a novice, you can start off with PubMed and Google Scholar, but there are multiple other databases that you can go to. And then on those databases, you build search strategies using tools of search such as Boolean operators, sorry, mesh terms. You can then download those results into referencing software like Mendeley, EndNote, or you can download it in Ryan, which is an online AI-based tool that helps you manage screen and develop a report for your systematic review. And what you basically do, whether you use any referencing software or you use Ryan, once you have all the articles downloaded in a certain software, you look at the title and abstract and you screen out the articles, you remove the duplicates, and then you go for a full text review on the final articles that you select. On the final articles that you select, you apply something called as data extraction forms, and then you develop something called as a table. In that table, you also develop that table using the PICOS guideline. Simultaneously, you also calculate the risk of bias when you're doing that. And then eventually you go for something called as the qualitative analysis of review. The qualitative analysis of review that you do can then be of multiple times. It can be a thematic analysis, it can be a narrative analysis, it can be a framework based analysis. And then you can have multiple approaches in this inductive approach, deductive approach, all that. So right now we are here. We have done all this. And like I've said, if you are a novice and you're starting off early, the best way to do a systematic review is to copy one that has been done more than 5 years ago. Any systematic review that has been done more than 5 years ago, you can do it if it has not been repeated. Why? Because if you take up a meta-analysis or systematic review that has been done before, you already know that that topic has been published. So if you do something around that topic, it can be published. Secondly, you know that there is enough data available. And then you also have a reference article to go back to every time you get stuck at any part of the process. Once you have done a review like this, then I would recommend that you can independently do any type of review, but you must understand that not all your qualitative reviews can be converted into quantitative meta-analysis because of certain factors that we will discuss today. Today is more along the lines of theory and understanding the knowledge base of a meta-analysis. And tomorrow is all practical about meta-analysis. So these are the key steps of conducting a systematic review. Um, the reason why I go to this slide every single day is because you must know what this is. You must know the key steps that you have to follow from the very beginning till the very end if you are to publish successfully. There's one thing that is not written here is the registration. You must register the protocol of your meta-analysis on a portal called as Prospero. You can also do it on Cochrane. But then if you register it in Cochrane, then it becomes a Cochrane review. So you should be willing to publish on the Cochrane library. Otherwise, you can use Prospero, and the primary guideline that we use for systematic reviews is Prisma guideline. We have been through this. We have discussed all of this in previous days. This is the Prisma flow diagram. This is the Prisma checklist. These are Boolean operators, mesh terms, online databases. And then we have also given you a case study that we will be looking at today. We will be looking at the main tables of this case study today. Simultaneously, we have given you tools that you can apply for your search builder. We have given you hands-on experience on using advanced search strategy, using filters, and all that. How data should be extracted. This is coming from the Cochrane handbook. So we have covered this as well previously. So that was day one. On day two, we had a very focused approach towards risk of bias, in that we applied the risk of bias tool by Cochrane using the visualization tool RobVis. And then we move towards a Newcastle Tower scale, which used a star-based approach for cohort and case control study, primary studies, if they were to be included in the systematic review. And then you develop a grid based on the stars that are assigned to for every aspect of that primary study. We also looked at Ryan, which is a systematic review management tool, and that is a very comprehensive tool for qualitative systematic reviews, and you can easily do it. You can use the paid version of Ryan as well. The paid version has its own benefits. These are two videos. You can all these presentations have been made available through the Google Drive. You can just go through the Google Drive. The previous 2 day sessions have been made available in the form of a video in the Google Drive. So you can just go through the Google Drive. You will find day one, day two, the videos. You will also find all the links in the presentation. The PDF presentation is available in the Google Drive. You can go through these tutorials of Ryan. They will help you a lot. They're not very big, 15 minutes long. With that being said, we did look up some bit of EndNote. If we get time today, we will go through EndNote. I don't want to spend a lot of time on EndNote because we already covered things through Ryan. But if you guys want, we can go through EndNote as well. Because I know now a lot of people are using Mendeley as well. So EndNote might be redundant for them. Similarly, thematic analysis, narrative analysis, framework synthesis, we discussed all that, integrating the qualitative findings with the quantitative findings. So this is a recap of what we have done up to in day one and day two. And I think now we have a good enough quorum. We are around 9 people. We can start off on day three. Day three and day four are all about meta-analysis. So no more talk about the boring systematic reviews. Now we discuss the boring meta-analysis. So with that being said, one of the core fundamentals that you must know when you're doing a meta-analysis is that not every study can be converted, not every review can be converted into a meta-analysis. And why is that? The primary reason for that is one word, and that word is heterogeneity. And heterogeneity is basically, in essence, means you guys have heard the word homogeneity, and you guys have heard the word heterogeneity. Uh, So heterogeneity and homogeneity, how are they different? Heterogeneity means differences in the studies. in the primary studies that you include in the meta-analysis. Homogeneity means similarity in the studies that you include in the meta-analysis. Now, heterogeneity can be based on clinical characteristics. So maybe the for example, say you are testing a drug in the primary study, and that drugs are clinically very different. So you cannot compare those drugs, or maybe there is a surgical intervention, or maybe there is a medical intervention, or maybe there's a psychiatric intervention, and those interventions are non-comparable with one another clinically. That could be one form of heterogeneity, which is the clinical, based on clinical characteristics. Another form of heterogeneity is the based on methodological characters. For example, one studies cohort, other is case control, and other is RCT. Within RCT, one is fixed effect model, one is parallel design, another is factorial design. So just to give you an idea, there could be a lot of methodological differences. So all those things are there. But even when the studies have the same clinical characteristics, they have the same methodology. Even then, there could be differences in the effect sizes. And in order to look at the differences in the effect sizes, we use Cochrane Q, we use I square, we also use tau square. So we use all these. So let's delve into. So we know clinical heterogeneity differences. We don't want to go into the detail of that. That's more like a clinical discussion. Methodological characteristics of individual studies is basically differences in their study design or differences in the methodological robustness of primary studies that you can look up by reading up on study designs. So both of these are not what we are going to cover here. What we primarily will cover here will be this heterogeneity, which is differences in the effect sizes of the individual studies included in the meta-analysis. And so, with that being said, the first measure of heterogeneity of effect sizes is the Cochrane Q, the Q test. And the Cochrane Q is basically it's a statistical test. So, what does it do? It basically determines whether the variation in the effect size among the studies means if there are, like, say, 4 studies. So, the variation in their effect sizes, and we'll discuss what effect sizes are so you don't have to worry about what effect sizes are. Okay. So, the variation in the 4 effect sizes, is that because of chance or is that because of heterogeneity? Are these studies actually statistically different from one another in terms of effect sizes? Or are these studies basically different because of chance alone? And in order to assess that, we go through calculation of Cochrane test. Now, any meta-analysis that you see cannot be complete without the Cochrane Q. It's a mandatory test for heterogeneity. It needs to be done because Cochrane Q leads to then I square. I square is again mandatory, so I square is heavily dependent on Cochrane Q, and we'll discuss how that is in upcoming slides. I hope this is not a lot of too much of statistics. I will try to make it as easy as I possibly can. But you must understand that Cochrane Q is basically applied because we want to know whether or not the effect sizes between the individual studies are they different because of chance or are they different because of heterogeneity? Means that they are actually different. So, what is an effect size? An effect size is basically, say, a standardized mean difference. So, you have two groups of people, men and women, and you give them a drug, and then you see the mean difference in the overall outcome. So, that could be the mean, standardized mean difference, or it could be correlation coefficient, how one thing is correlated with another, how the drug that you are giving is correlated with, say, life expectancy. So how are they correlated one another? So correlation coefficients come in there. Or Your effect size could be odds ratio, or they could be risk ratios for that matter. Um, Odds ratio and risk ratio, you can easily go online and learn what they are. Uh, Basically, odds ratios are mostly applied to studies that are case control studies, but they can also be applied in studies where you are trying to look at the exposure of something. And risk ratios are studies where you're trying to look at the effect of a certain intervention or effect of a certain exposure on the outcome. The outcome can be positive, the outcome can be negative. So those are risk ratios. I hope this is not too much. I will keep going on. In case you have a question, you can raise your hand in the middle or you can type it in the chat box. So how do we calculate Cochrane Q? First, we calculate the effect size. The effect size, every study already has its effect size. Maybe it is reporting the mean difference. Maybe it's reporting correlation coefficient. Maybe it's reporting odds ratio. Maybe it's reporting relative risk. So it depends on the study. And then you compute the weighted mean effect. What does that mean? So if there are four studies, you compute their overall effect size. Overall effect size. So you compute their overall effect size, and then you assess the heterogeneity. You calculate the Q statistic. How do you do that? By summing up the difference between each study's effect size, so with the overall effect size, and you weight it by the inverse of variance. Now, what does that mean? So this is the effect size of the study itself minus the overall effect size, and then you square this, and then you multiply it by the inverse of the variance. Inverse of variance means that this one study, how varied it is, right? How much of a confidence interval does it have? How much variable it is compared to other studies? And we look at the inverse of variance. Why? We'll discuss that in upcoming slides as well. Why inverse variance is so important here. But basically, what we are doing here is that we are taking the difference of the effect size of the study minus the overall effect size, and taking the square of it and then multiplying it by the inverse of the variance. And this is done for one study. And then you add it with a similar approach for all the other studies. So you have 9 studies, so this bracket is repeated again, and you sum the overall statistic. Now, the Q statistic, whatever the result that you get of the Q statistic, right, it is plotted on a chi-square distribution. A chi-square distribution is a right-tailed distribution. It looks something like this, right? There is a tail on the right side. So there's a bulk at the start. This is a normal distribution, just so that everyone knows. In a normal, sorry, these lines are coming up, but basically normal distribution is a bell-shaped distribution, something like this. Ignore these spikes. So a normal distribution basically says that majority of the people lie in the middle, and then there are outliers at the sides. This is what a normal distribution tells us. A right-tailed distribution says that the majority are on the left side of the graph, and then we have outliers on the right side. Chi-square distribution is applied for different aspects. Whenever we apply chi-square distribution, we always calculate degrees of freedom, because the Q statistic is based on chi-square distribution. Therefore, uh, we also calculate the degree of freedom. Now, mind you, you don't have to do any of this. The software, which is RevMan, will do all of this. All you have to do is just input data, and then it will do the rest. So then why should you know this? You should know this because this gives you the baseline understanding of what a Cochrane Q is. Okay, so if the Q statistic is significantly large, that means that the p-value is above a predetermined significance level. Means if we have, say, oftenly we keep the p-value as 0.05. We say that if the p-value is less than 0.05, then whatever result that we get is significant. What does that mean? That whatever result that we get is not because of chance, but rather it is a true representation of the population. So if the Cochrane statistic, we present the value of the Cochrane statistic as p-value. Why? Because again, like I said, because we plot the value of the Cochrane Q on the chi-square distribution. So the eventual result that we get is something like a p-value, and we can assess if it is less than 0.05, we say that there is significant heterogeneity. But if it is more than 0.05, it means that the Q statistic is not significantly large. So if it is less than 0.05, then it means that there is more variability in the effect sizes than that would be expected by chance alone, indicating heterogeneity among studies. That being said, there is an inherent problem with Cochrane Q. I won't say inherent problem, but rather a limitation that we need to the limitation is that when the number of studies is small, we will be unable to detect the heterogeneity. That's a limitation of Cochrane Q. And in order to solve that, we can then calculate I square. We can then also do subgroup analysis. We can also do meta regression. So with less number of studies, the sensitivity of the Cochrane Q decreases. We can also look at forest plot to have understanding. We will discuss what forest plot is as we move along. Today is all about this. So this was all about Cochrane Q. I hope this was not too much of theory, but basically, when we are to assess heterogeneity, the most important is Cochrane Q and I square. So then, if Cochrane Q is whether or not, I hope all of you can hear me. Can all of you hear me?
Yes, we can
Oh,
hear you, Dr. Hasan.
okay, great. So moving on. So if the Cochrane Q is basically telling you whether or not the effect size, the variation in the effect size of the individual studies is because of chance alone, or it's actually a difference. There is actually variation. Because if there's a lot of variation in the effect sizes of the individual studies taken into the meta-analysis, then we cannot do a meta-analysis. Then we will conclude with a systematic review. On the other hand, what is I square? I square basically is dependent on Cochrane Q. But what I square does is basically it calculates a proportion of the total variation in the study estimate. So think of it like this. If this is the total variation in the overall studies, this is 100%, right? So what percentage of this total variation in the effect sizes, what percentage, what proportion of this variation of the effect sizes of individual studies can be because of heterogeneity, and what percentage or proportion, percentage and proportion is basically the same thing, is because of chance. In case the heterogeneity of in case of I squared, we calculated between 0 and 100, like I said. In case it is, for example, if this is the total 100%, this is 25%, this is 50%, this is 75%, right? So in case it is 25%, we call it low heterogeneity. In case it is 50%, we call it moderate heterogeneity. Up till here, we can easily do a meta-analysis. But in case we have more than 50% heterogeneity, then there is substantial heterogeneity. And in case above it is 75%, then it is considerable heterogeneity. Normally, what we do is for low heterogeneity, up till like 25%, we go for fixed effect model. When we are, what is fixed? We will go into what is fixed effect model later on, just now in the slide. But when the heterogeneity is say above 25% up to like 75%, we go for random effect model. And if it's above 75%, then obviously we might do a meta-analysis, but we might not report the findings because they will have no value. So with that being said, this is I square. So the important thing here is not the calculation of Cochrane Q or I square, but the interpretation. The interpretation of Cochrane Q, like I said, is like the interpretation of p-value. You just check if it is less than 0.05 or not. The interpretation of I square is in percentage. Think of it like correlation coefficient, right? So 25, 50, 75, and then 100%. A high value indicates, a high value of I square indicates that there's substantial proportion of observed variability in effect sizes due to factors other than chance alone. So maybe the sample sizes are very big, maybe the confidence interval are too large, whatever the case might be. The sample sizes are too small, confidence intervals too large. So Dr. Kinzer is saying repeat the limitation of Cochrane Q. The limitation of Cochrane Q is primarily this, that when the number of studies is small. So, for example, say we have the total number of studies included in the meta-analysis. I don't know what the cutoff is, but you can assume, say the cutoff is somewhere around when the number of studies is less than 10. Then the Cochrane Q will give you the result, right? But the problem is that the sensitivity of this test might be weak. So there might be heterogeneity, but you might not be able to detect that heterogeneity. So in such cases, the researcher may still visually inspect the forest plot. Why will you inspect the forest plot? We will see in upcoming slide. And you will also calculate I square, because I square then gives you a more visual understanding because it gives you a proportion of the overall heterogeneity. So like I said, I square is giving you this proportion of heterogeneity, right? So if p-value is less than 0.05, it means that the Cochrane Q is coming out to be significant. It means that we have heterogeneity. So if the Cochrane Q, so think of it like this, the null hypothesis in this case, this is a very good question by Ms. Noreen. Thank you for this question. The null hypothesis is that there is no heterogeneity. The alternate hypothesis is that there is heterogeneity. So basically, if you're getting a significant result, if the p-value is less than 0.05, it means that there is heterogeneity. You understand? Because it depends on what is the alternate and what is the null hypothesis. In case of meta-analysis, we keep the null hypothesis as no heterogeneity and the alternate as heterogeneity. I hope this is able to, I was able to explain. It has been a learning curve for me as well to learn all these things as I delve into multiple experiences of doing meta-analysis. So it's important to note that I square alone does not provide information about the directness or the source of heterogeneity. For that, you might have to do a subgroup analysis or a meta-regression. Even if you don't do a subgroup analysis in your meta-analysis, still you can easily publish, but it is mandatory to do a Cochrane Q and a I square. The I square obviously complements the Cochrane Q, providing a measure of the magnitude of the heterogeneity in the meta-analysis. Like I said, it basically gives you a visual representation, a proportional, a percentage value to understand where the Cochrane Q is. The I square quantifies the extent of heterogeneity. Together, these statistics help researchers assess the robustness and the generalizability of the meta-analytic findings. There is another statistic of heterogeneity. It is called as the tau square. Now, the tau square is basically applied for studies where we apply random effect model. So we already know that it is those studies in which there is a significant, there is heterogeneity that we are seeing in I square. And we'll discuss how fixed effect model and random effect model are different and where we apply them um, in the upcoming slides. First, I will delve into what is tau square. So tau square is a measure of the amount of heterogeneity among the effect sizes of the studies included in the meta-analysis, which is quite similar to what we talked about for Cochrane Q. But the thing is that tau square is primarily applied on it's a you look at heterogeneity when you're looking at the random effect model. You then look at tau square, then tau square becomes significant. And basically, the random effect model assumes that the true effect size varies from study to study. What does that mean? Well, that means that if this is one study, two study, three study, four studies, they might be from different type of populations. There might be inherent difference in the overall populations that you are taking these studies from and you're doing these, even though the interventions might be the same, but there's an inherent difference in the populations. And so we assume when we are applying random effect model that there is a inherent difference in these studies in terms of the population sizes, in terms of the sample sizes. In fixed effect model, we assume that all of these are taken from the same type of population. Be it, say, you're looking at uh, kidney patients or so on and so on. Now, the overall effect size in random effect model is the weighted average of the individual effect size, where the weights are determined by the inverse of the sum of the study variance. Like I said before, I've discussed this. Uh, Inverse of variance is taken everywhere. Why? Because as you increase the variance, the sample size decreases. Now, we want to give more weightage to studies, primary studies that have higher sample size in the meta-analysis. Therefore, we take the inverse of variance. We don't take variance. So we take sort of like the opposite of variance, to put it simply. Now, this is how variance is calculated. Variance is basically calculated for tau square. Again, you don't need to know all this, but I want to get you through this because you understand. So, variance of I basically means the effect size of the ith study, whatever study that you have, say the fourth study, the fifth study, the sixth study. And WI is basically the weight assigned to this study. And so it's the sum of the weight assigned minus the variance divided by the overall sum of the weight assigned. That's how the overall effect size for random effects is calculated, and then that leads us to tau square. And then within tau square, like we said, the formula for tau square again takes into account the Cochrane Q. So as you try to understand everything, whether it is tau square or I square, they are both dependent on Cochrane Q. And Cochrane Q basically tells us that by whatever the effect size that we are seeing, whatever the variation in the effect size that we are seeing, is that because of heterogeneity or is that because of chance? Basically, that's the total determination that we are trying to make. Um, Now, the formula for tau square involves difference between the observed overall variance and the expected variance under a fixed effect model. So this is the tau square formula for fixed effect model. Um, Overall, we normally apply tau square when we are dealing with random effect model, generally speaking. With that being said, I have already delved into what effect sizes are, but just to give you an idea, effect sizes are basically, you can think of them like maybe one number or maybe a range that tells you the overall effect of every study, the overall effect of, say, an intervention, how effective it is. And then obviously the effect sizes have to be weighted based on the sample size that they have. And we all know sample size are associated with confidence interval. So that's why they are also associated with variance. So that's why we talk about the inverse of variance again and again. Now, what are the different types of effect sizes? The effect size can be this standardized difference in between two means, which we call cohorts D. We can also use it using hedges G, which is again a difference in the sample size, mean difference in the sample size. Or it can be Pearson correlation. So Pearson R, which is the correlation coefficient. or it can be odds ratio, or the effect size can be risk ratio, or it can be partial eta square, which is basically we are getting it from if you're applying ANOVA, in which again we are looking at the variance in between three or more predictors. So moving on, so effect sizes in essence basically tell us what is the effect of the primary study that we have taken into the meta-analysis. The effect sizes provide a standardized metric that facilitates comparison and interpretation of the results. You might assume, okay, if we had calculated the Cochrane Q, why did we like plot it on, sorry, why did we like plot it on the chi-square distribution? We plotted on a chi-square distribution because whenever we get a statistic, we need to then compare it with a standardized scoring system or a standardized graph. The standardized graph in this case is not the normal distribution or the z distribution, but rather in this case it is the chi-square distribution, which is a right-tailed distribution. So I hope I was able to explain some bit of it. Some of it might be difficult to digest. I understand that. I have found day three to be boring for a lot of participants, but still I go through the theory because it is important. People love day four because they find day four to be much easy because it's basically practical implementation. It's doesn't have a lot of theory to it. I've already discussed about chi-square distribution. The chi-square distribution is often used in hypothesis testing. And when we apply it in case of the Cochrane Q, the Q test, we assume that the null hypothesis is that there is no significant difference in the effect size among the studies. And the alternate hypothesis is there a significant, okay, sorry. So initially what I was saying was a bit different from this. So let me stand corrected. The null hypothesis says that there is no difference in the effect sizes among the studies. Hence, it means that there is homogeneity. So the interpretation of Cochrane Q in this case is that if the Cochrane Q is, sorry, there is a participant. Let me just add the. So the what that basically means, the interpretation of the Cochrane Q is that if it is less than 0.05, there is no heterogeneity. If there is more than 0.05, the level of the p-value of Cochrane Q, then there is significant heterogeneity. So I stand corrected. Initially, what I had said was the exact opposite of this, just to give you a clarity on this. So because we are applying the chi-square distribution, so the null hypothesis in chi-square distribution means that there is no significant difference in the effect sizes, and the alternate says that there is significant heterogeneity in the overall effect sizes. With that being said, the overall theory is the same that we have discussed up till now. And we use the degrees of freedom whenever we are using chi-square distribution. So therefore, you see the degrees of freedom when we are calculating Cochrane Q in the formula of Cochrane Q. I have not given the formula here, but it's there. And then also in tau square, the formula is there. So with that being said, confidence interval of the overall effect sizes are also calculated in the meta-analysis. And then obviously, as we say that the confidence interval should not capture one. So it should not capture one. Otherwise, there is no significant difference in between maybe some sort of protective effect of a drug compared to the adverse effect, something like that. With that being said, this is coming from the case study that we had shared with you previously. And the case study that we had shared with you earlier, uh, it basically is about caseload midwifery. I had already requested all of you to please go and read. We have also put the case report, the case study, which is basically a meta-analysis, in the Google Drive as well. For any one of you who is, you can just go there and download from the Google Drive. So it talks about caseload midwifery. Caseload midwifery means that you are doing midwifery at the time of pregnancy, at the time of delivery, and post delivery. This is what caseload midwifery is compared to conventional midwifery, which is done at the time of delivery. So here, this is something called as the forest plot. It is coming from that article. You can look up in that article as well. In the forest plot, you must first be able to understand what are the key components of a forest plot. Okay, so think of it like this. This is the forest plot, this graph. Now, what it shows is basically first it shows the effect size that we have taken, and here the effect size that we have taken is risk ratio. We can also look at the mean difference. We can also look at odds ratio. In this case, in case of risk ratio, one means that there is no significant difference in between caseload and standard care. This is what it basically means. Now, if you look at this diamond shape, the diamond shape represents the overall, the summative estimate of the effect size. So, this basically tells us the overall effect size, the cumulative effect size of all of these studies. Okay, so this diamond shape represents this. Now, as you see, this is one study. And as you look at this study, this line represents the confidence interval of that study. This line is the confidence interval of that study. If you look at these boxes represent the sample size. The larger the box, the larger the sample size, and the larger the weight of this study in the overall estimate, in the overall diamond shape. So let me just discard this and coming back here again. So, like I said, this diamond shape, it represents what? It represents the overall effect size, the total effect size with a 95% confidence interval. We keep it at 0.05%. The alpha error that we are willing to permit in this case is 5%. So the p-value comes out to be 0.05%. So the first thing you need to look at whenever you're seeing a forest plot is this. So basically, if this is a risk ratio, a relative risk, then one represents that there is no difference in between standard care or caseload. In case, and what are we looking at here? We are looking at perinatal mortality in this one. In the next one, we are looking at APGAR score, but here we are looking at perinatal mortality. So we are seeing, is the caseload midwifery, the caseload midwifery, which is the midwifery done pregnancy at the time of delivery and after birth, does it have an effect in on perinatal mortality? If it is reducing the risk ratio, the risk of perinatal mortality, it means that caseload midwifery is protecting against the perinatal mortality compared to the standard care. But if you look at the first study, the confidence interval, this line, is capturing one. Similarly, study two is also capturing one, three, four. So basically, overall, there is no significant difference in caseload midwifery and standard care when it comes to protecting against perinatal mortality. This is what it graph tells us. Similarly, if we can also see this, we can also see the risk ratios here. So for the first study, it is 0.33, which you can say is very good. But the problem is, again, the confidence interval is capturing one. In all these cases, the confidence intervals are capturing one. For the overall effect size, the diamond shape, again, it is capturing one. Now, as you look at this column represents the weights that are assigned to individual studies. For example, this was study number one, which was done in 2020, study number two, three, and four. Study number one has a weight of 6.4%. Study number two has a weight of 34%. Study number three has a weight of 34%. Study number five has a weight of 25%. Now, why is it that some studies have a higher weight compared to other studies? It is basically because of the sample sizes. You look at these sample sizes. So you can divide it into this represents the standard care, the total event of perinatal mortality that happened in the people who are receiving standard care, of the total people who received standard care, compared to the perinatal mortality that happened to people who are receiving caseload mortality. So these are the events of perinatal mortality in the total number of people who are receiving caseload midwifery. And this study had a sample size of 1156 plus 1158. And if you look at the total number of patients or people who received caseload midwifery was 2,700 compared to again 2,700 in standard care. So both these groups are quite similar, number one. Number two, there is difference in the sample size of individual studies, but then their weights have been adjusted for that. And so first we saw the forest plot, we saw the confidence interval in the forest plot, we saw the sample sizes, we saw the cumulative effect size, we saw what how do we interpret this, then and based on the risk ratio. And then we looked at the weights that were assigned to each study based on the sample size that it had. And then we also looked at we can also look at the heterogeneity. Now we have discussed heterogeneity. Like we said, tau square is interpreted like Cochrane Q, and basically it says that the p-value for the Cochrane Q here and for the tau square it's coming out to be zero point 0.0. So it's statistically significant. It means that for a random effect model, the result that we are seeing is statistically significant. But at the same time, it is also capturing confidence intervals capturing one, so we know it's not. Similarly, if you look at the value of I square, the first, if you look at uh, chi-square degrees of freedom, again, they are necessary for the Cochrane Q. So an estimate of the p-value coming from Cochrane Q is 0.93. So this is not significant. And if you look at the I square, which basically gives a percentage of the heterogeneity, it is 0%. It means that there is not a lot of heterogeneity, but again, even though there is not a lot of heterogeneity, because the confidence intervals are capturing one, the results are not significant. So level of significance is something else, magnitude of the heterogeneity is something else. And if you look at the overall effect size, we see that the p-value is 0.85. Again, it is more than 0.05. So hence it means that there is heterogeneity. So I'll just, yes, weights are specified as per sample size. And the weights are calculated by taking the overall effect size and multiplying it by the inverse of variance. And so that is how it is done. Uh, you can go back to the formula and see it. But in essence, basically, this is how it is, inverse of variance. I've tried to explain the the forest plot, which is this forest plot is this graph, and I've tried to explain this table of the meta-analysis for just one of the analysis. This is one analysis which is perinatal mortality. And there is another subgroup analysis that they did, which was for APGAR score. Again, this also didn't come out to be significant by this was capturing one. They did another similar subgroup analysis for perinatal tier. Perinatal tier for caseload midwifery compared to standard care. And we saw that again, the confidence intervals are capturing one in this case. And we can also see it here. For the and this was grade 1 to grade 4. For grade 3 and grade 4 perinatal tier, they again did something. And so what you're seeing here right now is a subgroup analysis in which they have created different subgroups for different variables, and they're looking at their effect sizes and their overall effect, cumulative effect on the, because they're trying to assess whether or not caseload midwifery has any benefit or not. So if you look here as well on the perinatal tier, grade 3 and grade 4, again, all of them are capturing one, and the diamond shape is very clear. The cumulative is again not significant. Similarly, for bleeding more than 1 liter at the time of delivery for caseload midwifery compared to standard care, again, it is capturing one. Even though this is slightly better, but again, um, this is like you look at the p-value. The p-value is 0.06. So it's slightly missing, slightly above 0.05. So again, uh, we don't have any significant. So, like I said, the Cochrane Q is not coming out to be significant here. So, in essence, what this basically means is that the results that we are seeing, there is no significant improvement in the overall outcome. There's no significant difference in the overall outcome for standard care and caseload. Um, Similarly, if you look at cesarean section, so the occurrence of cesarean section in caseload midwifery compared to standard care. So for caseload midwifery, the again it is not significant. You can look at, also keep on looking at the I-square values. Forgot to mention this. So even those at some places they are 0%, 0%. Here they are 54%. But look at the p-value. So the overall effect size, the overall p-value for the overall effect size is again not coming out to be significant. So just give me 1 second, please. Sorry. So apology for that. So in the meanwhile, this is done in 2 to 3 studies, so it is acceptable. What is done in 2 to 3 studies? Please explain. Sorry, I didn't understand. This is just one study. The results that you're seeing here are just for one study. These are multiple subgroup analysis that were done in that study. So look, it is written subgroup here, subgroup here. So so basically the primary thing that the study was looking at was mortality of female compared to the mortality of the child, mortality of the child for caseload midwifery. But what we see here is that in none of these forest plots, and even if you look at the level of significance, none of them are coming out to be significant. And for some, even the I-square values are high, like for example, 57%, 54%. So there is considerable heterogeneity. With that being said, we are going to now discuss what is fixed effect model and random effect model. And sir, for some of the variables, they have taken 2 studies, while for others, 3 to 4 studies are taken. Is it okay to take different number of studies for different variables? Yes, the reason is actually the subgroup in the subgroup analysis, studies will change. Why? Because not every study is calculating instrument birth. Not every study is calculating cesarean section. Not every study is calculating preterm birth. And that's the reason for doing the subgroup analysis. So, for example, the APGAR score was only calculated in 2 studies. But if you look at the perinatal mortality, it was calculated in 4 studies. But I think the overall studies that they took was somewhere around 8 or 9. So there might be overlap for some subgroup analysis in between studies, but there might be not. So for every subgroup analysis that we do, or in essence, for every forest plot that we develop, the studies can be completely different. Yeah, within the same meta-analysis. Yes. Okay. With that being said, what is the difference between fixed effect model and random effect? Both fixed effect and random effect model are used to synthesize data for the studies. However, there is a difference. The difference is that the assumption in fixed effect model is that all the included studies are drawn from the same underlying population, that any observed difference in the effect sizes are due to sampling error. They're not due to the population itself. So there might be something wrong in the way we didn't calculate the right sample size. The sample size was not significant. Maybe there was some issue with the sampling strategy. Maybe the way we did the analysis, they did the analysis, there might be something associated with that. That's the assumption in fixed effect model. From random effect model, it relaxes the assumption of fixed effect model by allowing for possibility that the true effect size may vary across studies. So the assumption is that the true effect size in random effect model might be different for individual studies. So there might be a lot of variance in true, but still we would like to do a meta-analysis. That's what I'm saying now. If the I-square value is above 25% to up to around 75%, we can go for a random effect model. But for a fixed effect model, we definitely then have to stick with I-square value of less than 25%. You guys can read up the details of all these models later on. They're all in the presentation, and you can look through it in the Google Drive. So it's already 1 hour has passed, and I know that there is like we have covered a lot of theory. I hope this was not too much for one day. And like I said, I found that day three is actually quite boring for people. So with that being said, forest plot and funnel diagram, what are they? So forest plots, we have already seen a forest plot. So basically, they are used to display the effect sizes, such as odds ratio, risk ratio, mean difference, along with their confidence interval for each individual study and the overall effect size estimate. So we have already seen what it is. Interpretation is that the position of each study's point estimate relative to the overall effect size provides information about the direction and the magnitude of the effect in that study. The width of each confidence interval indicates the precision of each effect estimate. Again, like I said, precision is sort of like the inverse of variance. So what it in essence means is that the larger the confidence interval, the more the variance, and the more the smaller the sample size. So forest plots allow for visual inspection of consistency of effect sizes across studies and identification of the potential outliers and or individual studies. There's also something that we do, which is funnel plot. Funnel plots are basically they are used to detect publication bias. And publication bias, how do we do it? It's basically an inverted funnel. It's something like this. We look at the normal shape of that should be like a triangle. Think of it like this: the overall studies that are published uh, on a specific area, they should follow something like a normal distribution. So most of the studies should lie in the middle, and some studies should be here on one side, some studies should be here on the other. But if you look at the funnel plot and the funnel plots is something like this, or if you look at the funnel plot as something like this, then it means that there is asymmetry in the funnel plot. And this shows a gap and skewness on one side and may indicate the presence of publication bias or other biases that affect smaller studies disproportionately. Funnel plots are often used accompanied by Eggers test and Beck's test for to detect publication bias. I will not go into the details of these, and personally, I have not really tested and played with Eggers test and Beck's test a lot. So normally we just look at the funnel plot to detect publication bias. This is an example of a forest plot. We I showed you previously the forest plot for the case study that we have. but this is the overall cumulative effect, the overall estimate. And these are the individual studies, one, two, all these studies. These are the overall odds ratio of these studies. These are the weights assigned. And as you can see, the higher weight is assigned to higher sample size. You can see the sample size, this bigger the square. And then because of that, you can also see the confidence interval is small. And as the sample size is small, you can see that the confidence interval is large. And you can see that being repeated again and again. So this is just to give you an idea of forest plot. We have already covered it in the case report. And like I said, the funnel plot is like an inverted funnel. You can see here, you can see here. And you can see that the funnel plot is used to assess publication bias. So in the first one, what you can see is that the y-axis represents sample sizes. So these are the sample sizes, and this is the risk ratio. And one means that there is no difference, zero point 0.1 to 1, zero point 0 basically means anything that is beyond this, it favors the control, and anything that is below this, it favors the treatment. And as we see that as the sample size increases, most of the studies are near to the one. You can see that here. As the sample size increases, look at this, right? Like I said, you will see this again and again that most of the studies lie somewhere in the middle. But if you look at this, there is an emptiness here. So, say these are studies with 250 plus sample sizes, these are studies with 150 plus sample sizes. So, any study above this line is 150 plus, any study above this line is 250 plus sample size, right? But if you see here, the studies below 150, you see that there is a gap. There's a gap where we see that there is disproportionately more publication of studies that favor the treatment. Disproportionately more studies are being published for studies that favor the treatment. And if this was something that was like going up as we move, but for example, so this is the funnel should be something like this. If it's actually true representation. Why? Because if the majority, the bulk of the studies are showing that there is a significant difference, then that difference should be seen at higher sample sizes. But at higher sample sizes, we see that it is basically close to one. So if you see at higher sample, it's basically close to one. So we don't see any effect at higher sample sizes. And even at moderate sample sizes, don't see any effect. But at low sample sizes, we see that the treatment has a lot of effect. It means that there's something wrong. There is some sampling error that is happening here. There is some publication bias that is happening here because this is not a true representation of the population. So I hope this funnel plot was able to help you understand what publication bias is and how we can detect it. And then that brings me probably to the last part of this whole theoretical hoggle boggle that we are trying to cover today. And so, what we are going to cover right now is subgroup analysis and sensitivity analysis. So, what is a subgroup analysis? And you already saw that in the case study that we covered, that the subgroups they covered perinatal tear, the subgroups they covered bleeding, the subgroups they covered preterm birth. So, within the overall infant mortality and maternal mortality, these subgroups were then delving into other outcome variables, right? So, so subgroups are when we start to subgroup analysis involves when we divide the studies included in the meta-analysis into subgroups. So we'll start to look at certain characteristics, like for example, we want to look at age, gender, study design, intervention type. In our case, we were changing the outcome again and again, and we are seeing whether or not there was a change or variation in the effect size in the overall effect estimate. So that's why we do the subgroup analysis, and you can see that we did the subgroup analysis here. You guys, when we do the tomorrow, when we do the The hands-on, we will also do the subgroup analysis. Today, if we have time, because we have some time left, we have around 50 minutes, we will actually do some bit of RevMan. So don't worry about it. We'll do that today as well if we have time. Apart from subgroup analysis, there is something called as sensitivity analysis. So what is sensitivity analysis? Sensitivity analysis basically examines the robustness of the meta-analysis results by systematically varying the inclusion and the exclusion criteria, the analytical method, and the assumptions. So how do we do that? Basically, the researcher conducts multiple analysis by altering one or more aspect of the meta-analysis methodology. For example, the researcher might exclude some studies which have a high risk of bias, or the researcher might use different effect size metrics. For example, here the researcher is using odds ratio. For example, in our case, the researcher is only using risk ratio. What if the researcher changed this to mean difference? Or maybe the researcher changes this to odds ratio. Obviously, for that, he would have to calculate all these things for individual studies as well, but that gives you more sensitivity, more understanding. The results of sensitivity in our analysis are compared to the main analysis to assess the consistency and the stability of the findings. Similarly, sensitivity analysis helps evaluate the influence of methodological decisions and assumptions. For example, for one effect size, say the overall effect estimate is coming out to be non-significant. But for another effect size, the overall effect estimate is coming out to be significant. So then that means that there is some issue with the methodological approach in the calculation of the effect size as well. So sensitivity analysis basically gives us robustness and reliability in our findings. Sensitivity analysis also helps us identify influential studies and outliers. So outliers might be there for, say, relative risk, but the same outliers might not be there, say, for mean difference, or the same outliers might not be there, say, for correlation. So that helps us. So example is excluding studies with high risk of bias, is sensitivity analysis, alternate effect size measurements, and statistical models. You can apply random effect model, fixed effect model. So this just gives you an idea on, so you learn to play with the data that you have in order to get to a certain understanding. We also do something called as a meta regression. What is a meta regression? Basically, the overall effect size that we see, all those effect sizes are coming from individual studies. Now, if the individual study has some confounders, this has some other confounders, this is some other confounders. Those confounders are basically clouding. Confounder is what? There is an exposure, and that exposure results in this outcome, or there is an intervention and then that intervention results in this outcome. And the confounder is basically a factor x, this is which is associated with the exposure, which is also associated with the outcome. And I'll give you an example. For example, we assume that coffee drinkers end up with pancreatic cancer, right? Coffee drinkers end up with pancreatic cancer, that is our assumption. We look at coffee drinkers and yes, they are having pancreatic cancer, but there is a factor X here, which is smoking, which we have not looked at. So, smoking, those who drink coffee mostly also are smokers, and smoking is basically causing pancreatic cancer. So, the causal pathway which leads from coffee to pancreatic cancer, smoking is not part of that causal pathway, but smoking is associated with the exposure, which is coffee drinking, and it is also associated with the outcome, which is the pancreatic cancer. Hence, it is a factor X. So these factor X, they cloud our judgment about associations. They cloud our judgment about the effects of a drug. And these confounders, in this case, the confounder is smoking, the confounder can be age, the confounder can be gender, the confounder can be educational status, and numerous other things can be confounders depending on the study that you have. So we do meta regression. In meta regression, something similar to regression, we adjust for confounders. So those confounders may lead to clouding our judgment about the overall effect size. It allows researchers to examine how study level characteristics covariates. Covariates are basically confounders may influence the magnitude and the direction of the effect. So the researchers select study level covariates based on theoretical consideration and prior evidence, and then they develop a regression model. You can develop a regression model easily in RevMan as well. You can also do that using Stata as well. And you can also do the meta-analysis in Stata as well. For our hands-on, we will be using RevMan because RevMan is recommended by the Cochrane distribution. So we are sticking with that, but you can easily do and get similar results using Stata as well. With that being said, meta regression, again, like I said, so it helps us to adjust for confounders. I'm not going to the detail of meta regression. Sometimes so whenever we are doing these fixed effect model and random effect model, right, we apply either a Mantel Hansel method or a Peto method. A Peto method is applied for fixed effect model. So normally when we have the outcome variable which is dichotomous, we apply the Peto method. Similarly, when it is dichotomous, we apply the Mantel Hansel method. But Mantel Hansel method is applied when we have a random effect model compared to Peto method when it is normally applied when we have fixed effect model. So basically, these are all, they help us in calculating the overall effect sizes. The cumulative effect sizes are developed using either a fixed effect model or a random effect model. Within a fixed effect model, we can apply a statistical method called as the Peto method and the random effect model called as the Mantel Hansel method. I know this must be too much detail, but just giving you the theory of this, and I'll just show you. Look at our case study, right? You see this MH being written here, right? And then you see this random effect model being here. See it everywhere, right? This MH is basically mental Hansel method applied with the random effect model in our case study. So for the sake of just discussion, mental Hansel method is a statistical technique which is used in meta-analysis and it is used to combine the individual studies. So basically, think of it like weighted estimates are calculated. Basically, the overall, that diamond shape, the aggregated estimate is calculated using mental Hansel method in random effect model. We also look at something called as inverse variance. We have been discussing this. So why calculate inverse variance? Why is all the weighing that we do, it is an inverse variance? Why is that? The inverse of variance, we calculate that, look, inverse of var, inverse of variance. Why? Because inverse variance is a fundamental principle in meta-analysis used to assign weights to individual studies. The rationale behind inverse variance is that studies with greater precision, i.e., smaller variance, means that they have a smaller deviation, contribute to the overall mode effect size. So, if a study has lesser confidence interval, it means that it has a larger sample size, larger square. It means that the overall it has a smaller variance. It also means that it has a greater precision, and hence it should have more weight on the overall effect size, right? So therefore, the variance, smaller the variance, more weight on the effect size. Therefore, we take the inverse of variance here. I hope I was able to clarify it. This is based on my understanding. When you're doing a meta-analysis, no one is going to ask you all this, but you should know all this theoretical part as well. There is also something called as observed minus expected variance in when we are doing meta-analysis. And what is that? The concept is basically particularly relevant meta-analysis of binary and dichotomous variables, where the studies often report the observed number of events and non-events, such as successes and failures. And Significance, the observed and the expected variance is a key component calculating the overall effect size in meta-analysis, particularly in fixed effect model. In fixed effect meta-analysis, the overall effect size estimate by pooling the individual study effect size with weight determined by the inverse of observed and expected variance. So it's not an inverse of just the variance, is the inverse of the observed variance minus the expected variance that we do for fixed effect model. There are limitations to it. I don't want to go into the detail of it, and that brings us to the end of day three. So right now we have somewhere around 40 minutes left in today's session, and let me just stop sharing. I know that what we have discussed right now is a lot of theory, and I know that this is this might be difficult to digest. But what I would recommend is that today go back to the presentation, and what I've written and these slides that I've developed have been developed to make it as easy as possible to understand what is everything. I want you to read this and I want you to read all of this and then interpret our study, the case study based on this, based on what is forest plot, what is a funnel diagram, what is random effect model, what is fixed effect model. Similarly, what is Cochrane Q, what is I square, what is tau square, what are effect sizes, what is chi-square distribution, all those things you should have an idea. And then obviously, why do we apply meta regression or subgroup analysis or sensitivity analysis? Why Peto method? Why do we do mental Hansel method? What is inverse variance weighing? Why inverse variance weighing? What is observed minus expected variance? And why is it used for weighing in what fixed effect model or random effect model? So that's about day three. If there are any questions, please go ahead and ask. I know that there might be this might be too much for one day, but we are short on time, so we have tried to cram things as much as we possibly can in the overall day three. So day three was all about theory. Um, okay, any questions? If not, then we can maybe start off with RevMan, or you guys want to take a break. Uh, So I leave it to Zishan, and then um, I leave it to who
Uh,
else, Amir or maybe Roshan. If you guys, what's your opinion?
yeah, sir, we can go with RevMan. It was
Okay.
a nice lecture.
So Dr. Sana is saying, please repeat yesterday's Ryan. I can repeat Ryan, but I think in the interest of time, let's go with RevMan today. We can do Ryan and EndNote tomorrow as well. We have tomorrow as well. So let's start off with RevMan because that would really help us. Okay. So what I will do is I will just share my screen. Okay. So let me. So this is the case that we have given you. You guys can easily go to we can do EndNote and we can do Ryan tomorrow. Those are basically for qualitative systematic reviews. We have actually moved ahead from there. We want to do for the quantitative part. So this is the basically the study that we have shared with you. And in this study, you guys can look at child and maternal benefits and risks of caseload midwifery, a systematic review and meta-analysis. This was published in 2023 in BMC, Pregnancy and Childbirth. And then I just went with you guys through the these are the what do we call the forest plot and the final analysis that were done for the meta-analysis in this study. So we went through this in the presentation. You guys can go through the whole presentation. This they have also given supplementary material. We have made that supplementary material available here in the Google Drive as well. All the supplementary material is available here. How they looked at risk of bias, how they looked at the search strategy, what was their exclusion criteria, and then obviously I have previously applied this on RevMan as well. So just to show you the so let's start with RevMan right from the very beginning. Okay. We have shared RevMan with all of you. How many of you have actually installed RevMan in your computer? That's something that I want to ask first. How many of you, let's have a show of hands, how many of you have RevMan installed in your computer? We have shared the RevMan software with you earlier. Please confirm if you have the RevMan software with you. We have shared it in the group. Please confirm if you don't have it. So I'm sharing the EndNote software again in the group, and I'm sharing the RevMan software. If you are on a Mac, you can use the RevMan Web. Don't worry about it. The software that we are sharing is for Windows. But if you are on a Mac, you can use RevMan Web. I am sharing in the WhatsApp group. I'm sharing the link of RevMan Web as well. Um, so in the group, I've shared RevMan Web. We have also shared um, the RevMan software. So let me just so a lot of people have this installed. No issue, just install it right now. We can give you guys 5 minutes to install it. Simply all you have to do is RevMan is an open source software. All you have to do is just basically go to the Google Drive link that we have shared. In this is the RevMan software. Download it first in your computer. You click here on the three dots and then you download it in your computer and then you install it. It is a very simple installation. We have also given this Google Word document, and that document has a few links, which are basically tutorials on how to use RevMan and then interpretation of the heterogeneity in meta-analysis. Also, we have given tutorials for that. You can easily go on YouTube and go through these links. They will, both RevMan Web and RevMan are the same. RevMan has now been discontinued. The only thing that is left is now RevMan Web. But a lot of people have difficulty with RevMan Web, so will first do everything on RevMan and then we'll go to RevMan Web. Okay, that is what we will do. I hope all of you are able to install it. So now what I will go is in order to do this, you guys need to open up the table, which is basically the first table of perinatal mortality, this one. And what we will do is that we will basically replicate this in RevMan just now, all of us together. And then we'll do this today and then other subgroup analysis tomorrow. Okay, so we will just do this. Yeah, standard mode is totally fine. Install it with the standard mode. You can, if you're on a Mac, if you are on an Apple device, you might not be, you can access the file by going on the Google Drive. The Google Drive has a open, it doesn't have any, it doesn't require any sign in. Basically, you can go there and download it, not an issue. The RevMan software is over there. I can see it in the Google Drive. All you have to do is first download it in your computer and then install it. First download in your computer and then install it. First, download in your computer, and then install it. First, download in your computer, and then install it. First, download in your computer, and then install it. First, download in your computer, and then install it. First, download in your computer, and then install it. First, download in your computer, and then install it. Okay. With that being said, let me open up my RevMan. So I'll just share the screen, and this is my RevMan software. I'll just open up RevMan. I hope all of you can see this RevMan. Now what I will do is I wanna basically replicate this table, and I wanna do this meta-analysis. I wanna create a forest plot and also a funnel plot using this. So what I will do is I will basically I hope all of you are able to see my screen. I'll go to my RevMan. I will go to File. I'll go to New. You all have to follow me in this. That's why I will go very, very slowly in this. So first off, I hope most of you have installed RevMan. Next, you go in File, you go in New, and then you go in the wizard. So you go in File, New, and then you go Next, and then it gives you different options. What is the type of review? In the type of review, you will click on intervention review. Why? Because the case study that we are following has intervention studies in it. You can also use studies that have done diagnostic test accuracy, or methodological reviews can also be done, or you can do other flexible reviews in which you might combine multiple study designs. In the interest of this workshop, for the sake of this, we will just stick with intervention review. So I'll click next. And then it says, so what is the intervention? The intervention is case load midwifery, and the health problem is, say, perinatal mortality. I hope all of you are able to see this and follow this. First, I went to RevMan, I clicked on File, I clicked on New, and then I clicked on Intervention Review, then I clicked Next, and in that the title was Caseload Midwifery for Perinatal Mortality, and then I clicked Next, and then it says, okay, fine. So what stage are you on? Are you on protocol stage or full review? We are going to be on the full review. If you click on full review, then you click on finish, and then something like this will open up. How many of you have come up to this window where you can actually see that meta-analysis? Please have a show of hands or just put it in the chat box if you can see this. Okay, so Dr. Sana is here. Okay, who else? We need 5 or 7 people to be at this place, to be on this window, where you have started with the new RevMan, you started the RevMan, got into File, got into New, Intervention, and then you clicked on Finish. I hope all of you have been able to do this. Once we do this, I'll show you this. I have Mac, okay. Afshana, so in Mac, you can just go on RevMan Web. So just go on RevMan Web. Here you go, RevMan Web. As you go on RevMan Web, you need to create an account. The reason why I was not trying to go into RevMan Web right now is I will not delve into RevMan Web right now because the people who are doing on the RevMan software will then get confused. Let me just first go through RevMan software, and then all those who are unable to have the software, they can wait. Okay. And then after that, I'll go through the RevMan Web as well. No problem. It's basically the same thing. That's a web-based server, and this is basically on your own computer. So I hope all of you are here on this window. I hope we can move forward. This is also being recorded, so all of you can go back to this and learn. Okay. So then once you are here, you have basically started off caseload midwifery for perinatal mortality. You'll click on the studies that you have included. And so you'll click here on the studies and references. Within this, you'll click on included studies. I'll just double click on this. And in this, you'll click on data and analysis. So studies and references in this data and analysis. Sorry, you have to right click on this. Um, so let me repeat it again. You come here, you click on studies and it was something like this, studies and references, right? You click on studies and references, right? And then once you have clicked on this, reference to studies will open up. And in this, you can add a study. Reference to studies, and then you will add a study. You will add the study in included studies. Let me repeat it again. If you were here on this intervention review, you will click on studies and references. In this reference to studies, you will right click, you will right click and then go into add study. Right click and go into add study. It will give you the option of included studies. You will click next. And the study ID, you can basically put this Fernandez 2020, the first one, this one, Fernandez 2020. Okay. So I go back to my RevMan. I say Fernandez 2020. I hope all of you are able to follow me, and I click next. So then it says, okay, so the data source, is it published only, published, unpublished, whatever. So published only because it is already published. I wrote Fernandez 2020 over there, so it picked up 2020 from there. I'll click next. You don't have to add any identifiers for now. It says, what do you want to do after the visit is closed? We will add a reference of a new study. So we'll add a reference and then continue. So we basically add a new study, include studies, click next. We will add another study. So the next study that we will add, the next study will be Homer 2001, this one. Homer 2001. So I go back to RevMan and I write Homer 2001. Hit next, publish data only, next, next. And then I will add another study and then continue. And then the next study that we'll add will be this McLachlan 2012, the third one. McLachlan 2012. It doesn't really matter if you get the names wrong, doesn't matter. Just follow my lead for now. So 2012. Next, 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 add reference, add study. So the next study that we'll add will be the last one, which will be Tracy 2013. You guys can see it here. Tracy 2013. So I'll go here, I'll write Tracy 2013. Next, next. And then what happens after you finish it? Do nothing, right? That's it. So we have first, we created a reference, we created a meta-analysis, then we added studies into it, right? And then within these included studies, you can see multiple studies. We have Fernandez, Homer, McLachlan, and Tracy, right? Now we'll go into data and analysis. First, we went into reference and studies. So studies and references here, studies and references within this references studies, and we did add a study. We added the study. You can add included studies. You can add excluded studies. Then RevMan can actually create a report for you. And then once you have done, we have put in all the studies that we wanted to put in. You can see it here. So the next thing we'll do is we'll go into data and analysis, and then we'll say add a comparison. So data and analysis, add a comparison. And in that, I'll just give it a name. I'll give it a name which is perinatal mortality. And I'll click next. What do you want to do? Add outcome under the new comparison, continue. So I hope all of you are able to see me. In case, follow me. In case you are not able to do it, don't worry about it. We went into data and analysis. We went into add a comparison and data and analysis, add a comparison, and then we went into we wrote perinatal mortality, and then we wrote next. What do you want to do? We want to add outcome under the new comparison. We click continue, and then it says, okay, what type of outcome do you have? Do you have a dichotomous outcome, which means you have a binary outcome, yes and no? Or you have a continuous outcome, or you want to look at the variance, or you want to look at the observed minus expected outcome, or you just want to look at the generic inverse variance, or you want to work with something else. So we have a dichotomous outcome. Why do we have a dichotomous outcome? Look at this. Either the person has perinatal mortality or does not have perinatal mortality. Either the mother dies during birth or does not die during birth for caseload midwifery or for standard care. Simply put, that is the outcome that we are going for. So dichotomous. Next, they say, okay, fine, now give it a name. So I'll just give it a name of perinatal mortality. Okay, they say, okay, fine, give it a label of the group. So I'll just say this is caseload. Group number one, which is the experimental one, is caseload midwifery. And group number two, which is basically standard care. So I'll give these groups and then I'll click next. And then it says, you know what? Okay, fine. What type of statistical method you want to apply? Now you guys will understand why that theory was important. So we will not apply Peto method. Why? Because you are going for a random effect model. And in the random effect model, we are going for a random effect model. Why? Because previously that is what the study has done. For the sake of argument, we are following this. Why? Because there was a variance in between the effect sizes. Therefore, they went for a random effect model. And because we are going for a random effect model, we apply a mental Hensel method. Why? Because it is used for dichotomous variables. When we are applying a random effect model, we can apply a Peto method when we are doing a fixed effect model. At the same time, they say, you know what type of effect measure do you want to check? So for the primary studies that you select for the meta-analysis, right? Whatever is the effect size over there, you can use it. In our case, because the the case study that we are using is using risk ratio, so we will also use risk ratio. So in this, we'll apply a risk ratio. We can also do a sensitivity analysis later on and apply odds ratio by looking at primary studies and see if we can get odds ratio out of those studies. And then we can go for this. Okay, so risk ratio, mental Hensel statistical method, analysis model, random effect model. Next. Okay, so what is we are going for totals and subtotals. What is the confidence interval? We are going for 95% confidence interval. This is what the study has done, and arbitrarily, this is the most common one that we apply. You can go for 99% or 90%, but generally, this is what is recommended 95%. Total confidence interval, again, we are going for 95%. We click on next. So then it says, okay, so what will the graph look like? So and how do you want to sort this? We want to sort this by effect size. Okay, and how would the graph look like? Well, the graph should say favors caseload of favors, control की जगह we will just write standard care. Why am I doing that? Because I'm basically just trying to replicate favors caseload, favors standard care as was in the study that we are trying to replicate. This is what we're doing right now, the graph, this graph. Okay. There is a comment. How do we enter data from our database? I'll show you how you enter data. Just follow my lead for now and just so then you click next and then it says edit the new outcome or do nothing. So I can just say, I can say finish, edit the new outcome. So edit the new outcome and then finish. And this is what I see right now. What I'm seeing right now is that this right here is your empty shell that we have created for the meta-analysis in which no study has been added in this table and then no study and then we are not seeing any forest plot. So first thing first, I hope all of you have been able to come here. You can see this is the outcome that we are looking at is perinatal mortality. You can add multiple outcomes here as well. So now what I'll do is I'll add new studies in this. How? This plus sign here with a green mark, I'll click here. And then it says, okay, what do you want to add? I want to add Fernandez. And then I'll press control and I'll click all four of these and I want to add them. So I said finish and look, all these studies are now part of my overall analysis. Now what I will do is I will start entering data for all of them, right? How will I enter data for all of them? So for Fernandez 2020, let's just add the data from the file that we have. So this is the data. I want all of you to enter data into this. So for Fernandez, for caseload midwifery, there was 0 event and there was total 169. And for standard care, there was 1 event and the total was 165. So 0, 169 and 1, 165. So what I'll do is I'll just come here, 0, 169 and then 1, 165. I'm just entering data here. And then the next thing is, okay, the next study was Homer 2001. What I will do is just come here, Homer 2001. The data is for caseload midwifery 4, 550. So 4 perinatal mortality out of 550 in caseload midwifery. And for standard care, 4, 539. So 4, 550 and 4, 539. So I'll just go here, 4, 550 and then 4, 539. Okay. The next one is McLachlan 2012. So I'll just go here. In McLachlan, they had 4 cases in 1156 participants in caseload midwifery and 4 cases for perinatal mortality in 1158. So 4 1156 and then 4 1158. So I'll just enter 4 1156 and 4 1158. Literally the same type of thing you can do in Stata very easily. And you can easily get the code of Stata very easily online. You can do the same thing on Stata if you are uncomfortable with RevMan. RevMan is also very easy. You can use RevMan as well. So last study is Tracy 2013, in which the data is 3 perinatal mortality out of 871 in caseload and 3 out of 877. 3 871 and 3 877. So I'll just put the data here. 3 871 3 877. And then I'll click here and I can now see you can see this risk ratio. Now let me just compare this with this. Oops. I hope all of you can see my screen. Now look at this. Look at the forest plot that was there in the published article and look at the forest plot that we have created. Exactly identical. If you have been able to follow my lead, if you have been able to do the same thing, you will come up with the same forest plot. If you have done this forest plot, basically you have completed your first meta-analysis. Obviously, this is one table. You can develop multiple tables, but basically this is you have completed your first meta-analysis. And the interpretation that we had previously done for risk ratios, look at this interpretation. So I'll just keep it here. Look at the interpretation here. So we have a weight of 6.4%. Let me just put it here. So for the first study, the weight was 6.4%, second was 34.1, third was 34.0, and the last was 25. Same. And we are getting similar risk ratios. Everything is just the same, right? And you can also look at the tau square value. You can also look at the overall p value. You can also look at the I square value. All of them are here. Now, what you can also do here is you don't just have to stay with the forest plot. This is the forest plot, right? What you're seeing here, you the graph and everything. This is from us, right? You can also look at other things. For example, you can look at this you can look at the funnel plot. So the funnel plot for this, if you can see, is look as we are moving. So they for this they have used a standard error. So standard error is as good as sample size. You don't have to worry about it because standard error increases as sample size decreases. So if they have given the standard error here on the y-axis, this is as good as the sample size. And in the lower range, they have given the relative risk. And as you can see, for this perinatal mortality decreases for caseload midwifery in lower sample sizes. But for higher sample sizes, in which there is a smaller amount of standard error, you will see that there is no difference. Basically, it's capturing one. So we see that again, you can say maybe there's publication bias at lower sample sizes, but not at higher. And so this was, so we calculated, we looked at the forest plot, we looked at the funnel plot. We did this for risk, we can do it for risk difference, we can do it for odds ratio, we can do it for multiple ones. Okay, so we can do it for odds ratio as well. So we talked about sensitivity analysis, right? You can do it for relative risk. So this is risk ratio, relative risk. You can do it for risk difference. You can also do it for so this is the risk difference with the random effect model, and this is the risk difference with the fixed effect model. And you can also do the odds ratio with the Mansell handle and fixed effect model, and you can also do it the risk ratio for, but again it depends on whether or not the primary studies have showcased risk ratio. Even if they have not, you can easily calculate this because, well, you have the cases and the overall controls, and then you have the occurrence of the event that you're looking at. So you can easily do a sensitivity analysis here. You can easily do a subgroup analysis. How you can do a subgroup analysis? Simply put, you start off by doing another analysis to add a comparison, and then you can go on and add a comparison for this APGAR score. You can add a comparison for perinatal tear and all that, bleeding, and go on and on. You can basically replicate the whole thing. So please repeat the fixed effect, the random effect model in these results. Okay. So if you go to RevMan, and if you're on RevMan, all you have to do is first you have entered data. If you want to look at, so this is random effect model risk difference. If I click here, risk odds ratio for it shows random effect model, and it shows odds ratio, risk ratio for random effect model. And if I click again, so this is for random effect. And if I click it, this is for fixed effect risk difference, fixed effect risk difference. Yes. So this is for the risk difference, and this is for the odds ratio, random effect. And then you can also look at other things. You can also add other variables. For example, you can look at the log of the odds ratio. You can look at the log of the risk ratio, log of the confidence interval. You can do a Pareto odds calculation as well. Um, the purpose is of all of this is to first, number one, if you look at this heterogeneity, look at heterogeneity. The other is look at the effect sizes and look at whether or not those effect sizes are coming out to be significant or not by looking at the confidence interval. Okay, so this is basically what there is, but you can add other data as well. For example, so right now we are for looking at risk difference. Let's just move to random effect, um, random effect and risk ratio. Sorry, risk ratio. Yes, here you go. So for risk ratio, this is what the study had provided, and so they also give you an idea of what is the chance of uh, uh, the overall risk of bias. But for that, you need to enter data for individual studies. We didn't enter data for risk of bias. So you will see the risk of bias as well here in this if you want. Generally, that is not required because we already develop a risk of bias in the risk of bias visualization tool. So that's generally not needed. We have already looked at the interpretation. The interpretation of this is basically that there is no significant difference in between caseload midwifery and standard care if you want to reduce perinatal mortality. Why? Because all of them are capturing, all of the confidence intervals are capturing one. Um, we can see that there is some deviation for smaller sample sizes, which basically favors caseload, but overall, there is no significant difference in between caseload and standard care. You can see the effect sizes here based on the sample sizes or the inverse of variance, inverse of the standard error. And then this is the overall cumulative mean risk ratio that you're seeing for these studies. The heterogeneity, tau square, chi square, heterogeneity tau square, and then Cochrane Q, and then I square are given here. For Cochrane Q, you can look at the test of the overall effect. It is coming out to be insignificant. And for I square, it is 0%. So even though the magnitude wise, we don't see heterogeneity, but overall it's coming out to be insignificant. So this is the overall interpretation. I hope this was helpful. I'll stop here. If there are more questions, we can take those questions. I'll stop the recording here as well.